Okay, so now I'm going to go over the concept of Nash equilibrium. In general, this will be the guideline for us to solve static games. Okay, or roughly speaking, for any static game, we want to find its Nash equilibrium. So let's try to do this. So first, we need to give you a precise definition of Nash equilibrium. So suppose there is a game with n players. Okay, there can be any number of players. For each player, there must be an action space. Let's call it Si. Si contains all those possible actions of player I, and each player should have a utility function Ui. Ui is a function of actions. Okay, so whenever we have an action profile, which is a collection of actions, let's call it S1 up to Sn, then we have a utility function. A utility can be decided by put those actions into the utility function. Okay, so generally speaking, that means my utility depends on other players' utilities. Maybe some of them, but anyway, in general, it can depend on all the players' action. Okay, so my payoff is affected by other guys. Now, for a Nash equilibrium to happen, we require the following thing. That is, suppose a profile is a Nash equilibrium, then that means if all other players do not change their action, okay, if they are still sticking into S1 star up to Sn star, if all other guys do not deviate, then I will also not deviate. Okay, originally I am choosing Si star, and then because Si star is the utility for me to take Si star is greater than or equal to any other Si. Okay, so that means if others do not deviate, then I do not deviate. If that's true for all the players, then it is a Nash equilibrium. Okay, so another way to write it down is the following. For all the players, if the player try to solve the optimization problem for selecting an action, then given those other guys' actions, my action would be that in the utility in the Nash equilibrium. Okay, so either this or that. That's the mathematical definition of Nash equilibrium. But anyway, the intuition is, if we say an action profile is a Nash equilibrium, then no player has an incentive to unilaterally deviate. This term is just means to deviate when no other guys deviate. Okay, we will see examples. Here you see a term pure strategy. We'll talk about it later. So let's consider this example. Here we have two players, each has three actions. So player 1 choose T, M, or B. Player 2 choose left, center, or right. There are in total 9 action profiles. Okay, TL, TC, TR, up to BR. Is there any Nash equilibrium? Let's try to see it. For TL, okay, they get 0 and 4. In this case, this is not a Nash equilibrium because player 1 has the incentive to move to M. Here, this is unilaterally deviation. Okay, player 1 will think, okay, currently we are at TL. If player 2 does not deviate, then I would move to M because 4-0 gives me a higher utility than 0-4. The same thing happens to TC. Okay, if currently they are at TC, player 2 would think, okay, if player 1 sticks to T, I would like to move to either R or L. because 4 is greater than 0, 3 is greater than 0. Okay, so this is also not a Nash equilibrium. You may go through all these action profiles until you see BR. BR is a Nash equilibrium because if player 2 stays at R, I have no incentive to move to C. If player 2 stays at R, I have no incentive to move to M or T because 6 is greater than 5 and 5. Player 2 is the same thing. Okay, so we can show that there's only one Nash equilibrium in this game. Sometimes we say a Nash equilibrium is an outcome of this game. That means we predict this guy is going to do this decision. Of course, that's based on an assumption that they interact for many iterations, or we say they do that in their brain for many times. Okay, think very deeply before they make the final action. But at least we can say a Nash equilibrium is a stable outcome, because once that happens, unless they coordinate, then no one is going to change their decision. Let's see some more example. For the prisoner's dilemma, we may again, for each of the action profile, to verify whether it is a Nash equilibrium. This one is not, because player 1 has the incentive to unilaterally deviate. 0 is greater than -1. For denial and confession is again not, because player 2 has the player 1 has the incentive to move to confession, because 6 is greater than -6 is greater than -9. This is the same, and then we can see confession and confession is a Nash equilibrium. Player 1 does not want to move to denial because that's going to get him only -9. Player 2 does not want to move to denial because he does not want to get -9. Similarly, we may investigate the other game we mentioned in the previous video. Here, how about BB? BB is a Nash equilibrium, okay, because 2 and 1 are greater than 0 and 0. And then SS is a Nash equilibrium, but BS or SB are not. Okay, so this means this game has 2 Nash equilibria. For the last game, we can do some investigation and immediately you will see there is no Nash equilibrium. So we got 3 examples: a unique Nash equilibrium, multiple Nash equilibria, or no Nash equilibrium. All are possible. Actually, the previous slides is not rigorous enough because we only talk about pure strategy Nash equilibrium. But if we allow randomized or mixed strategy, things will be different. Okay, what's this? Let's look at this game again. Actually, this is just a simplified version of scissors, paper, stone, right? Because in either situation, one wins or one loses. If we look at this game, actually there is one strategy. That strategy is to randomly choose head or tail, right? There's no one saying that you must make your decision about choosing head 100% or to choose tail for 100%. You can say that you want to choose a decision variable P, okay, P, which is the probability for you to choose head. And then naturally 1 minus P yours is your probability for choosing T. The other player can choose Q and 1 minus Q as his probability for choosing head and tail. And then this game is going to become 2 decision problems. Player 1 solves for P and player 2 solves for Q for the optimal strategy or the optimal probability to choose head. Anyway, what my point here is just that if we allow randomized strategy, then the strategy space will be much larger than when we only allow pure strategy, right? Even if we only have two actions, the strategy space is actually infinite because we have a whole line segment. Okay, you can choose P to be 0, 0 0.1, 0 0.2.6, 0.26, or 0.3114. No, that's all possible. So, under this assumption, in 1950, John Nash proved the following theorem regarding the existence of mixed strategy Nash equilibrium. Given any static game, if the number of players is finite and the action space are all finite, then there must be at least one mixed strategy Nash equilibrium. This proposition is very important because it shows that for a wide class of games, or for static games, we can find at least one mixed strategy Nash equilibrium. And then that's going to help us applying this concept, right? Because if the concept is so strict that for many games we don't have a Nash equilibrium, then it's not very useful. But because we have this proposition, then the whole field of game theory start to build things upon this concept. So this is one of the most important findings in economics in the past 60 or 70 years. Okay. Actually, in this course, we will try ourselves to avoid mixed strategy Nash equilibrium. Most of the time, we will only focus on cases where we have pure strategy Nash equilibria. This is because we are really facing business applications, right? If we are making decisions, somehow we need to make a choice. You cannot say to your supplier that, with probability 1/2, tomorrow give me 100 units, or with probability 1/2, tomorrow give me 200 units. You cannot make this kind of random order to your suppliers. You somehow need to make a decision. So in most of the applications we study in this course, we only focus on pure strategy Nash equilibria. But still, I hope you to know there are pure strategy pure strategy Nash equilibrium, mixed strategy Nash equilibrium, and the foundations there. Okay, let's stop here. Thank you.